All right, so we're going to continue where we left off, talking about correlation. Okay, make sure I get caught up here. All right, so some properties of R, some things that we can add to our understanding of R. R itself is only between -1 and 1. You can't have anything bigger than 1. An R of 0 means there is no linear relationship there, that we can't, X does not predict Y, there's pretty much nothing there. If we have something between 0 and 0.5 or 0 and -0.5, we get to use the word weak. We get to say that's a weak correlation. Anything between 0.5 and 0.8, both positive negative side, we get to say moderate. And if it's between 0.8 and 1, we get to say strong. So -0.8 and -1 also strong. Okay. All right, so we're going to go back to our calculator and look at some properties of R for just a second. So we're going to type in this data. I'm going to scroll my calculator over here. And I'm going to tell you that these are in terms of millimeters, which at this particular moment is not relevant, but it will be in a moment. So we're just going to take a second and type in those numbers. Let me get started here. Okay, so 12, 15, 21, 32, 26, 19, 25. This is quick enough, I guess, that I can just do it real. 4, 7, 10, 14, 9, 8, and 12. Okay, so we're going to find R. So let's quit out of this. Go to our, go to Stat, Calc, and let's calculate the R. And I'm not going to worry about storing the equation for right now. We will need that eventually. All right, and I calculate R, and I get an R of 0.918. Okay, so you want to remember that for just a second. Now it's asking us to switch this to centimeters. So what's the relationship between millimeters and centimeters? Millimeters is there's 1,000 in a meter. Centimeters is 100 in a meter. So I essentially want to take all of those numbers and multiply by 10. So if I go back to stat edit, and we'll just make another list, list 3, where I want list 1 times 10. Okay, so let's see, so 10, highlight list 3, by the way, so go on top, highlight list 3, and just type 10 times list 1. It'll give me that new set of numbers, and then when I do my LSRL, I just want to tell it to go to list 3 instead of list 1. But other than that, it should be the same. So stat edit. And then let's see, switch this to list 3. And then go ahead and work it out. And so the only difference here is I changed my x's. I multiplied all my x's by 10 to see what would happen. And what do you notice about R? R is the exact same number. Remember, R is a measure of predictability. It's a linear predictableness. So if there's a linear relationship already the first time and I multiply the x's by 10, I didn't really change the relationship. So I get the same correlation. Okay. Let's look at this then. We're going to find a correlation between these two sets of numbers, and then we'll switch places with them and see if that makes a difference. Maybe that property will matter. So let me go ahead and clear out all of these, and I think at this point I won't force you to watch me type numbers in. So let me get all the numbers typed in, and then I'll restart the video. All right, so I've got them all typed in. We're going to find the R between list 1 and list 2. So let me go back to the home screen. And then, let's see, I need to switch this back to list 1. And then I'm going to input, calculate the R. And I get an R of 0.918. Yay. Now I'm going to switch the order and see, does that make an actual difference? So when I go to calculate, I'm going to tell it to actually go to list 2 for X and list 1 for Y. Ooh, very devious. And what do we notice? We notice we get the same R. Okay, so what does that tell us about switching X and Y? It means that you get the same R. But again, R is a measure of predictability. We're assuming it's a linear relationship, but does X predict Y, or does Y predict X? That's kind of what we're deciding here, is that we get the same sort of thing. Okay, now we're going to go in. Let me kind of show you that we're going to change one number, and it's that last number we changed from 12 to 22, and we look at what that relationship is. Does that make a difference? So let's go back to our stat edit and go all the way down to the bottom here. And so you can delete out that one number, or you could just type over it. Should be okay either way. And then we're going to go to our regression and calculate R. And then I need to tell the calculator I want list 1 to be X again. And I need list Y to be list 2. Okay, so then I'm going to hit enter and let it calculate R. And R changed, got worse actually. So you have to think about, well, what does that tell us about R? If adding an outlier affects correlation coefficient, that means R is a non-resistant measure. Outliers or extreme data have a huge influence, just like the mean and standard deviation. Extreme data impact those measures as well. Okay, we're going to find the correlation for these points. So let's do that. Go to stat edit. Alright, so let me speed this up so you don't watch me necessarily type in all of these numbers. Now, these are the same numbers that are on your handout, so you don't need me to you don't need to see my screen. Okay, just one word of caution that I discovered as I was trying to type it in is make sure when you're typing in negative numbers you use this negative button, not the subtract button. Calculator's really picky about which symbol you're using to indicate negative, so you always want to use this negative button down here. Okay, so we're going to start by calculating R and just confirm the strength of R here. It seems to be it's a really strong one. Okay, and when I calculate R, I get, actually, no, I get an R of 0, which means there is no predictability here. There's no relationship. Now, for kicks and giggles, let's go take a look at the picture of this. So let me go to zoom and then zoom stat. And even though R says there's no predictability here, I can see that there is some sort of relationship between the data. And so just pointing out that R might be 0, but there is a relationship. What we're looking at specifically is a linear relationship with R. So there's got to be some more things to R that we haven't looked at yet that'll help us sort of analyze this. Okay, so I want to end this particular video set with sort of a fun one. So I'm going to pull up another data set that we're going to do some analysis on. Okay, so little thought experiment. We're going to not thought experiment. There is a data set that's famous for illustrating the power of correlation. We've got a number of ministers in New England and the amount of rum that was imported to Boston. And this is historical data. This is actually factual. We're going to type in the calculator and look at the R and the relationship that exists here. So we're going to do the number of ministers is our X, and the alcohol in Boston is our Y. So we're going to type that information in. So let me give you a second to do that. Okay, so I finally got it all typed in there, and we're going to look at the correlation coefficient between the number of ministers and the alcohol in town. And I guess as I'm doing this, what do you think is going to happen? You kind of think, that's kind of a weird question. Why would we do that? So as I calculate this, we find that the correlation coefficient is 0.99. It is a strong predictor. Now that's something to think about. Why would the number of ministers be able to predict the amount of alcohol in the town? Is there some other strange relationship going on? And so what I want to do with this, as we're sitting here thinking, is does an increase in ministers cause an increase in consumption of alcohol? Does one thing cause another? Is that what correlation really tells us? Is it a cause and effect thing? And so I want you to think about three thoughts for just a second, and they are: number one, correlation does not imply causation. Simply because it's predictable doesn't mean it causes it. Number two is correlation does not imply causation. And the last thing, and hold off before you jump to the gun there, correlation does not imply causation. Just because two things are predictable does not mean that there is a cause and effect relationship going on here. Okay. These are some fun, and you can Google this yourself and get 10 interesting correlations that are out there. So this is just a collection of interesting patterns that people have noticed, not necessarily noticed, but have, if you play with data, you can notice, oh wait, this thing has a relationship with this. So these are all things that have a strong correlation with one another. Ice cream apparently leads to murder. A pirate shortage causes global warming. Won't talk about that one. Let's see. M. Night Shyamalan. Shyamalan? Wow, said that interestingly. Makes bad movies because people don't buy newspapers. So there's a relationship between that. Using the Internet Explorer leads to murder. Okay. Mexican lemon imports prevent highway deaths. So these are all interesting little correlations out there. So anyways, the point being, just because one thing seems to be related to another isn't necessarily true. There's actually another concept out there called a lurking variable. Okay, so sort of the last thought out there, and this kind of is a scary name now that we think about it. Whenever we do see that sort of relationship, that one item seems to be connected to another, it could be a third party. There could be another variable that's actually impacting the other two, and we just don't know what that variable is. So whenever that sort of relationship is discovered, we refer to that as what's called a lurking variable. Lurking, like it's in the dark. Ooh, it's going to get you. Anyway, so lurking variable. There we go.